There is a region of space 330 million light-years across that contains almost nothing. By every model of how the universe distributes matter, it should hold thousands of galaxies. It holds roughly 60. The Boötes Void sits 700 million light-years from Earth in the direction of the constellation Boötes, the herdsman. It is not a gap between structures. It is not a shadow cast by something closer. It is a sphere of absence so vast that light leaving one side at the moment of the Big Bang would still not have reached the other. And inside it, the rules that govern how matter collects, how gravity sculpts, how galaxies cluster, seem to have been switched off for the age of the universe. On the largest scales, matter is arranged in what cosmologists call the cosmic web, a three-dimensional lattice of filaments, walls, and nodes, with galaxies strung along the threads like dew on silk. Between those filaments are voids. They are a natural consequence of gravity operating over billions of years, pulling matter into denser regions and leaving behind pockets of relative emptiness. A typical cosmic void might span 100 million light-years. It would contain fewer galaxies than the surrounding filaments, but it would still contain galaxies, scattered, faint, but present. The voids are low-density regions. They are not vacuums. The Boötes Void is something else. In 1981, astronomer Robert Kirshner and his colleagues were conducting a survey of galaxy redshifts, measuring how fast galaxies recede from Earth, to build a three-dimensional map of their positions. What they found in the direction of Boötes was a hole, not a subtle underdensity, not a statistical dip in the expected galaxy count, but a hole. A volume of space roughly 250 million light-years across, later revised upward to 330 million, in which the galaxy count dropped to nearly zero. The initial discovery was startling, but it was also uncertain. Redshift surveys in the early 1980s were limited in depth. It was possible the void was an artifact of incomplete data, a gap in the survey rather than a gap in reality. Better instruments confirmed it. Through the 80s and the 90s, deeper surveys filled in the surrounding cosmic web with increasing precision. The filaments sharpened. The walls became clearer. The void did not fill in. If anything, its boundaries became more defined, its interior more conspicuously empty. Roughly 60 galaxies have been identified inside the entire volume, 60. In a sphere that could comfortably hold 2,000 based on the average density of the observable universe. Astronomer Greg Aldering helped map the void's true scale. His observation, once the dimensions became clear, has become one of the most quoted lines in modern cosmology. If the Milky Way had been located at the center of the Boötes Void, human civilization would not have known that other galaxies existed until the 1960s. Every civilization that ever looked up at the sky, from ancient Mesopotamia to the European Enlightenment, would have seen only stars, their own stars. The rest of the universe would have been too far away to detect with anything less than the most powerful modern telescopes. The entire history of astronomy would have been settled in the wrong direction. One galaxy floating in infinite darkness. That is not poetic exaggeration. It is a geometric consequence. An observer at its center would experience a fundamentally different cosmos. The same physical laws, the same particles, the same forces, the same speed of light, but a different observable universe, shaped not by different physics, but by different context. The loneliness would be structural. The question that has followed the void since its discovery is straightforward, and no one has answered it. How did it get this empty? Cosmic voids form through a well-understood process. In the early universe, tiny fluctuations in density, imprinted during inflation, the brief period of exponential expansion just after the Big Bang, seeded regions that were slightly denser or slightly less dense than average. Over billions of years, gravity amplified those differences. Denser regions pulled in more matter, becoming filaments and clusters. Less dense regions lost matter to their surroundings, becoming voids. The process is called gravitational evacuation, and it works reliably in simulations, but it works slowly. Gravity is the weakest of the four fundamental forces, and it operates across distances that light itself takes millions of years to cross. The rate at which a void can grow depends on the density contrast at its boundary and the time available. For the standard cosmological model, the one that accurately predicts the cosmic microwave background, the distribution of galaxy clusters, and the expansion rate of the universe, the maximum size a void can reach in 13.8 billion years is well constrained. The Boötes Void exceeds that constraint, not slightly, significantly. The standard model can produce voids of 100 million light-years without difficulty. It can stretch, with favorable initial conditions, to perhaps 150 million light-years. 330 million light-years, with an interior this empty, requires either initial conditions that the standard model does not predict, or a physical process that the standard model does not contain. Several proposals have been put forward. None have been accepted. One class of explanation adjusts the initial conditions. If the inflationary period contained rare, extreme fluctuations larger than standard models assume, the seed for a void this size could have been planted in the first fraction of a second. These non-standard inflation models are mathematically consistent, but they are constructed specifically to explain anomalies like the Boötes Void, which makes them difficult to test independently. A model built to predict one thing has not actually explained it. A second class invokes exotic dark energy. In the standard model, dark energy is uniform. It pushes space apart at the same rate everywhere. But some theorists have proposed that dark energy might behave differently in different regions, exerting a stronger repulsive effect inside voids and accelerating the evacuation of matter beyond what gravity alone could achieve. If true, it would rewrite the simplest and most successful model of cosmic acceleration. The Boötes Void would not just be a hole in the map, it would be a window into a different kind of physics. A third proposal is more conservative but no more satisfying. Perhaps the void is not a single structure at all, but a collection of smaller, overlapping voids aligned along the line of sight from Earth. Each individual void would fall within the normal range. Their overlap would create the illusion of a single, enormous absence. This explanation requires no new physics, but deeper surveys have not found the expected walls or filaments between the supposed subvoids. The interior remains smooth, conspicuously smooth. The cosmic web is the most successful large-scale model of the universe ever constructed. It predicts the positions of galaxy clusters, the temperature fluctuations in the cosmic microwave background, the statistical distribution of matter across billions of light-years. It is tested, confirmed, and refined by every major survey. And it does not predict the Boötes Void. Something emptied that region, or something prevented it from ever being filled. The physics did not stop working inside the Boötes Void, but whatever physics shaped, it may not be the physics written in the current models. Somewhere in the direction of the herdsman, there is a sphere of silence, 330 million light-years wide. Every instrument ever pointed at it has come back with the same answer. Almost nothing is there, and no one can explain why nothing chose that place to be.